Hi there, Mr. Sutton here with the Algebra 2 6-6 lesson on solving exponential and logarithmic equations. This will be a three-parter. In part 1, we will be solving exponential equations. In part 2, that'll be the logarithmic equations. And then in part 3, we will turn our attention to tackling exponential and logarithmic inequalities with lots of real-life problems thrown in all over the place. For our opening question, see if you can solve the following exponential equation. 3 to the 4x equals 3 to the 8. Pause the video, see if you can intuit this one out, and then we'll take a look at it. All right, so hopefully you kind of noticed that we have the same base on each side. These are both 3's. So if we have 3 to the something equaling 3 to something else, then the something and the something else, the 4x and the 8, it would stand to reason must have the same value, at least if these two things are equal. So another way of kind of going at this is if you have a common or same base, you can cancel those and then set your exponents equal to each other. So we can say 4x equals 8. And this is one way of doing this problem. And then obviously just divide by 4 and we get x equals 2. So for our next problem, we might notice here that we do not have a common base on each side, at least not right away. And you might wonder, well, what do we do in this situation? There's a few different approaches we can take, but we should always at least try to rewrite each side with a common base before canceling. So if you look at the left and right and see that they are both powers of the same number, maybe try rewriting them both as powers of that number. So pause the video and see if you can pick up what I'm putting down here, and we'll come back together and see what's going on. All right, so on the left and the right side here, I notice that we have powers of 10. 100 is really 10 squared, so I can write this as 10 squared to the x. And then over here, 1 over 10 is really 10 to the negative 1. So I'll write this as 10 to the negative 1 to the x minus 3. I don't quite have a common base yet. I mean, I sort of do, but what I really want to get is a situation where I have 10 to the just one single exponent equals 10 to just another exponent. I don't want all this parentheses baloney going on here. So I'm going to use my exponent rules to simplify this a little bit further. 10 to the 2 to the x, that's really, if you multiply these exponents, we have 10 to the 2x. And over here I can multiply these exponents as well. So that would give me 10 to the negative x plus 3. I have to distribute that negative 1 to both of those. Now that I have 10 to the something on each side, I can essentially cancel out the 10s and rewrite this as 2x equals negative x plus 3. And then I can add the x over to the left side to get all the x's together. And dividing both sides by 3, we get the very basic answer for something this complex looking, that x equals 1. So if you're feeling kind of good about that common base method for solving exponential equations, take a look at this next one. Notice anything different about this problem versus the last two? Well, yeah, 7 is not a power of 2. 2 and 7 don't really have a common base. I mean, 2 to something is going to give me 7, but it's nothing I can easily figure out without using a calculator. And the directions seem to indicate a calculator might be necessary, given this talk about decimals. So what happens if you don't have a common base? Well, in that situation, we can turn to logarithms. If there is no common base, then we can use logs, specifically the pop-out rule, to isolate the variable. So if I take the log of each side, this x is going to come out as a multiplier. So pause the video with that little hint and see if you can figure out how to get to our answer. All right, so taking the log of each side, on the left side I'm going to have x log of 2 because I popped out that x as a multiplier. On the right side I've just got log of 7. Nothing really special going on there. To isolate x now, I just have to divide both sides by the log of 2. Now this whole expression log of 2, that whole thing is just one crazy decimal. So that moves as a normal number would. So we've got log of 7 divided by log of 2. And at this point I'm going to have to go to the calculator and see what that actually comes out to 3 decimals. So plugging this in my calculator, let me make a fraction here, and then I'll do log of 7 divided by log of 2. And that comes out to about 2.807. Now, if you want, you can always check your answer by plugging it back in. So let's see what happens if I take 2 and raise it to roughly 2.807, and that gives me pretty close to 7, which is what we would expect. Now, one other thing that's kind of cool, worth noting here, is that although I used the common base 10 log here, I didn't have to. I could have used any log as long as I used the same base on both sides. I could use ln even. If I did, let me do a fraction here, ln of 7 divided by ln of 2, you'll notice that I still get the same answer. So use whichever one is most easy or comfortable for you in the situation. For this next problem, we have a real-life application that'll use these exponential equations. They want to know how long it takes for $250 to become $2,000 at 6% continuously compounded interest. So real quick, just pause the video and see if you can come up with a function that tells us how much money our $250 grows into after t years. All right, let's see if you got that far. So since we're using continuous compounding, we need our PERT formula here. Our principal in this case is the 250 that we're starting with. The rate is the 0.06 to represent the 6%. So we have 250e to the 0.06t. That's what our f of t equals. Now where do we go from here? Well, if we want to know how long it takes for this to become 2,000, we're trying to solve for a t value. And they're giving us a target f of t value of 2,000. So we can swap out f of t for 2,000. And this gives us a nice little exponential equation. Now, just as a little bit of a hint before you go ahead and solve this, it's always good to isolate the exponential term before taking the log of both sides. So with that little tip in mind, pause the video and see what will happen on this one. All right, so to isolate that exponential term, I've got 250 getting divided from both sides, so that's going to give us 8 on the other side. Now you might wonder, well, what happens if you don't isolate that exponential term? Well, usually nothing good. The long and short of it is it just takes you a lot longer and it's a lot messier. If you took the log of this right side, for example, without getting rid of this 250, then you would have log of 250 plus log of e to all this stuff, which is a little bit more of a mess to deal with. In general, I like to do everything I possibly can before I mess around with logarithms. So going a step further, there's another little tip that I'm going to give you at this point. We could take the regular common log base 10 of both sides, and that would actually get us the answer just fine. But a little shortcut you can take, if e is your base that you're trying to get rid of basically, then you can use the log for that, ln of x, in this situation. So I would have ln of 8 equals 0.06t times ln of e. Now you might wonder, well, what's the advantage of using ln of e instead of just log of e? Well, ln is the number I have to raise e to in order to get the expression inside. What do I have to raise e to in order to get e? Oh, well, this expression here is just 1. So basically, when you use ln on an equation that has an e in it, your e essentially gets canceled out, and you just get this 0.06t that was in the exponent. Because ln of e is just a 1, you don't have to write. You can still write it if you want to, though. In any case, solving for t, we're going to divide both sides by everything that's not t. In this case, that's going to just be the 0.06, because again, we said ln of e was just 1, so we don't have to worry about it. I will have to plug this stuff into my calculator, though. So we have fraction ln of 8, and we've got 0.06 down there, and that comes out to about 35 we'll round it off to 2 decimals, 66, and that's going to be years. So at 6% interest, it takes about 35 years for your 250 to become $2,000. So at this point, while you're waiting for your retirement account to come to fruition here, if you're doing the CP non-honors version of this lesson, this is the end of part 1. You can pause the video and solve some exponential equations. If you're doing the honors, then we have one more real-life application we're going to take a look at for part one. For this honors application of exponential equations, we're going to take a look at Newton's law of cooling, which is actually a pretty, no pun intended, cool way to use exponential equations. So Newton's law of cooling says that the temperature, big T, of a cooling substance after little t minutes can be modeled by this function. Big T equals T0 minus TR times e to the negative RT plus TR. Well, that's a whole lot of T going on there. In fact, one of the more common applications of the law of cooling is seeing how long T will take to cool. But forget about that. Too many T's. So what do all these T's mean? Well, we already saw that T was the actual temperature of a substance at a certain little t time. This T0, or T naught as they sometimes call it, is the initial temperature of the substance. This TR is the surrounding temperature, so the temperature, for example, of the room or air around the thing that's cooling. And then finally, this little r is the cooling rate of the substance. So we're going to use this in just a moment to figure out the time it takes some stew to cool. But just real quick, before we do that, just to appreciate sort of this law of cooling, it turns out that this actually works on things other than tea and soup. It actually works on solid objects cooling down as well, which is kind of neat. And it's also worth noting, because they mentioned temperature a bunch of times, you might be wondering, well, what unit of temperature is this? Fahrenheit, Celsius, Kelvin? It actually doesn't matter. It works for all of them as long as you use that unit consistently for all these big T's that you're plugging in temperatures for. So with all of that said, let's look at our problem. Let's say you're cooking some alicha, an Ethiopian stew. Looks yummy. Maybe you've got some of that spongy bread to soak it up with. When you take it off the stove, though, its temperature is 212 degrees Fahrenheit. Definitely not something you want to chomp into. The room temperature is 70 degrees, which seems reasonable. And our cooling rate is 0.046, which I have really no idea what that means. Is that maybe like 4.6%? Sure, let's go with it. We want to know how long it'll take to cool the stew to a serving temperature of 100 degrees Fahrenheit. So we're going to use our formula that we have up here, this cooling formula, Newton's law of cooling. We're going to plug some stuff into it. I actually would like you to pause the video for a moment and just plug things in where you think they belong, then unpause it and let's make sure we have things in the right place, and then we'll take the next step. All right, so for plugging things in, the only thing that I'm not plugging in anything for, since they asked how long, is this little t. So all the other t's and other things need to get things plugged in. This big T, that's the target temperature. They want to know how long it takes the stew to cool to 100 degrees. So that's going to be 100 for this just T without the little subscript. For the T0, T naught, the initial temperature, that was the 212 that our alicha started at. The surrounding temperature, the TR, this was the room temperature of 70 degrees. And maybe this R actually stands for room. I don't know. So we got minus 70 there. And R is already kind of spelled out for us. So we have e to the negative 0.046 T. Plus we've got the room temperature again of 70. So this is what we should be working with when we solve things. We're going to be solving for this little t. This is just kind of an exponential equation on steroids or possibly alicha. Either way, pause the video and see if you can find that little t value. All right, so a few things we're going to need to do on this first step. This 70's got to go. I'm going to move it over to the other side with the 100 by subtracting. So that'll be 30 over on the left. And I can combine the 212 and the 70 here. That's going to be 142 e to the negative 0.046 t. Next, I'm going to divide by 142 so I can fully isolate my exponential term. I'm just going to leave that as 30 over 142. I'm going to be using the calculator in a bit anyway, so there's really no reason to reduce or simplify this before I absolutely have to. Before I can do that, though, I need to take the log of both sides. Since I've got e, just like I did on the last problem, I'm going to use ln because that's a little bit easier when you're dealing with e. So we have ln of 30 over 142 equals negative 0.046t times the ln of e. The pop-out rule gets our t out of exponent land. And just like before, thankfully, ln of e is really just 1, so I can just kind of forget about it. And to get t, I just need to divide by this negative 0.046. So I've got ln of 30 over 142. That whole fraction is inside the ln. All of that divided by this negative number. Let's go to Desmos and see what happens. So let me make a little fraction here. In the numerator, I have ln of, open a parentheses, 30 divided by 142, close parentheses, and down in the denominator of this big fraction, I've got this negative 0.046. And that all comes out to about 33.8. So that's 33.8 minutes that it takes our stew to cool down. And that is it for this first section of the honors version of this lesson. This is the end, so go enjoy your Alicia, pause the video, do some exponential practice, and then come back. We're going to be doing logarithmic equations next. Welcome back to part 2 of this lesson. This time we're going to be talking about some logarithmic equations, and to kind of start off this conversation, we're going to talk about one of the main applications of logarithms, the Richter scale. So the Richter scale you might have heard of, that measures earthquake strength on a scale from 0 to 10. I mean, theoretically, you could have something stronger than a 10, but then probably the Earth isn't here anymore. The following formula relates the energy, E in joules, produced by an earthquake, and its rating M on the Richter scale. So log of E equals 4.4 plus 1.5 times M. So the question here, the Chilean earthquake of 1960 was the most powerful on record. It had a Richter scale rating of 9.5. That's pretty crazy. So here's some pictures, actual pictures that were taken after this earthquake. This thing was just absolutely devastating. The question we're curious about here is how much energy did this thing release according to this equation? So we've got this equation here. Pause the video and see if you can start working through this question. All right, so if we want to know how much energy we released, we're solving for E, so that means we have to replace M with this 9.5. And let's see, all we really have to do to get E, well, E is already by itself kind of sort of, it's trapped inside this log. We really just have to simplify this other side though as our next step. So let's go to Desmos and start doing that. So we've got 4.4 plus 1.5 times 9.5 comes out to 18.6. All right. And now what? So at this point, there's two approaches you could take. You might have already tried one of them based on an earlier lesson where we were trying to get things out of logarithms. You might remember when we were talking about inverses and we had like log of y equals something. One way to kind of flip the script on that, almost literally, is to turn this into exponent form. So if we're doing this, we have to recognize that log is really log base 10 if we don't write a number, so that's kind of important. And then if we write this in exponent form, we can keep our base of 10 and switch the input and the output, so we can write e equals 10 to the 18.65. And then we can plug that in the calculator. So doing 10 exponent 18.65, that's about 4.5 times 10 to the 18, and that's going to be in joules. Now there's another way of doing this, and this is the way I want to kind of emphasize on this lesson. I mean, exponent form's great. Just another way of thinking about it, though, is that we can raise the base, again, that's 10, to both sides of the equation. This is another option we have. So I can do 10 to the left side, 10 to the log base 10 of e, equals 10 to the 18.65. And just to kind of prove that this is legal, this is kind of the reverse of what we did at the beginning of this lesson. Remember there when we had common bases, we were allowed to cancel them out and set the exponents equal to each other. So this is just going the opposite direction. Now when we do this, remember that when we raise a base to a log with the same base, those two cancel each other out, leaving us whatever was inside. So this is just going to be e on the left side equals, well, we already figured out that 10 to the 18.65 was this number, 4.5 times 10 to the 18 joules. So this is another option we have, is raising that base to both sides. And just kind of as a reference to this amount here, because I mean, what does this even mean? This is actually 20 times the energy released by the strongest nuclear weapon that we currently have. And just for reference, about 50,000 times the strength of the nuclear weapon that was dropped on Hiroshima. So this is no joke right here. So here's another problem for you to try out. This one has a little bit more to it than the last one, but same kind of idea. Pick a technique, pause the video, and see what you can do with this one. Alright, so I've got the logarithmic expression already isolated. We've got one thing on the left side, one thing on the right side. This is the point at which we want to use one of those two techniques. So I'm going to keep raising the base to both sides just because it's kind of like a shiny new toy that I want to keep using. So I'm going to raise the base 2 to each side. So that's 2 to the log base 2 of 5x minus 17 equals 2 to the third. On the left side, the 2 and the log 2 are going to cancel out. So that's just 5x minus 17. And on the right side, 2 to the third is 8. Let's just go ahead and solve the rest of this now. Add 17 to the other side. We've got 25. And 25 divided by 5 gives us x equals 5. Or does it? So one thing that's a little bit tricky about these log expressions, you might recall that logs have a limited domain. Logs are undefined at 0 and negative inputs. If you remember the graph of a log, we have that asymptote as you approach the y-axis from the right side, and there was nothing in negative territory. So you always have to check by plugging your answers into this original to see if you get any of those extraneous roots. So if I plug 5 back in for x here, 5 times 5 is 25, minus 17, you could check to see if it actually all comes out to 3. The thing I'm looking for right now, though, is just making sure I'm not taking the log of 0 or a negative. And I'm definitely not. Log of 8 is a positive. So nothing's undefined at x equals 5, and I'm feeling good about our answer. So here's another problem. For this one, that whole turn it into exponential form thing doesn't work quite as well in this situation, but the other technique might work. Pause the video and see what you want to do on this one. Alright, so because we have base e, I'm going to raise e to both sides of this equation. The e and the ln are going to cancel each other out, so we end up with 4x minus 7 equals x plus 5. And then that's just going to be adding 7 to the other side. That's going to get us 12. Subtracting x to the left side gives us 3x. So we have 3x equals 12. And then dividing by 3, we have x equals 4. Plugging this back in, 4 times 4 minus 7 is a positive, so that's fine. 4 plus 5 is also positive, so that's good as well. Nothing undefined at x equals 4, so we're going to take that as our answer. Now, another way of kind of thinking about this, instead of raising e to both sides, you could just think of it as if you have a log equals a log and it's the same base, you can just kind of cancel out the logs. But this is really what's happening behind the scenes. We're going to do one more problem where we have to solve a logarithmic equation. On this one, we notice that we have two logs that are on the same side. So it's very tempting to just kind of dive right into raising both sides to the base. But you need to be careful when you do that, because that's not going to distribute over this addition here, so it's actually not going to work out the way you hope and think it will. Instead, you need to use your log properties to get one term on each side before you move to undo the logs completely. So our situation that we want to get to before any of our techniques is one thing on the left side, one thing on the right side. No pluses or minuses of things on either side. So pause the video, use your log rules, and let's see where this one takes you. Alright, so the rule that applies here, since I'm adding these logs together, that means I can multiply the items inside. So I'm going to have 2x times x minus 5. That's going to give me log of 2x squared minus 10x, and then we still have 2 over there. And at this point, I can either make this exponential form or just raise the base 10 to both sides. I'm just going to go with 10. So we have 10 to the left side equals 10 to the second. On the left side, that's going to be 2x squared minus 10x, because 10 and log cancel. On the right side, 10 squared is going to give me 100. And let me just move that 100 over to the left side. And now, to solve this, these are all divisible by 2, so I could either take out a common factor or divide everything by 2. This is a quadratic, so I'm going to go to my quadratic toolbox on this one. If I divide everything by 2, that'll give me x squared minus 5x minus 50 equals 0. And then looking for things that multiply to negative 50 and add up to negative 5. I mean, I could use quadratic formula, but I think I might be able to factor this one. So let me see here. 1 and 50 doesn't work. 2 and 25 doesn't work. 5 and 10 works if I have positive 5 and negative 10. So we can make this x plus 5 and x minus 10. And then zeroing each of these out, we see that x equals negative 5 or x equals positive 10. So we got two different answers. Or do we? Don't forget to check for extraneous roots. If I plug negative 5 into the original, 2 times negative 5 is going to give me a negative that I'm taking the log of, and the same thing happens over here. So because I'm taking the log of a negative, negative 5 actually makes the original undefined, and we have to cross that out as an extraneous root. Let's check 10 as well. We can't assume that there's going to be any answer at all. There could just be no solution. So 2 times 10 is fine. 10 minus 5 is also log of a positive, so that's fine. So 10 then is our final answer. So at this point, we have reached the end of part 2 for this lesson. Pause the video, do some logarithmic equations sort of practice, and then join us again when we tackle the inequalities. Welcome back. You're joining us now for part 3 of this lesson. In this one, we are doing the exponential and logarithmic inequalities. Now, the good news is the inequalities and the equations work pretty much the same way. You're going to solve these inequalities as you would using just the same techniques you would use for an equation. And you might be wondering, well, while I'm doing these techniques, what happens to my inequality direction? And the really good news is you're going to keep that symbol the same direction unless you multiply or divide by a negative, which has always been a thing. So unless you're doing one of those, you're just going to keep this facing the same direction from start to finish. So with that in mind, pause the video and do whatever it is you think you should do in this situation. All right, so since we've got an exponential equation, we either are thinking common base method or logs. 20 is not a power of 3, so I'm thinking logs are going to work better. Let's take the log of both sides. So that's going to be x log of 3 less than log of 20. And then that means that x is going to be less than 20 divided by the log of 3. Now, we do need to be a little bit careful when we're dividing by logs because some logs do have a negative value. Just to show you, the log of, log of 10 to the negative 1, for example. So log of 10 to the negative 1 is obviously negative 1. But if I were seeing this, I would probably see it as log of 1 divided by 10. That's probably how it would come up, or log of 0.1. And it would look positive because it's positive log, but the actual value would be negative. So just be careful and make sure that you really are dividing by a positive when you divide by the log of something. Anyway, we can write x is less than all this stuff, and let's actually calculate what that is. So we've got fraction log of 20 divided by log of 3, and that comes out to about 2.727. So x is less than that. Here's another example for you to play around with. Pause the video and give it a shot. All right, so let's first isolate the exponential term. So let's subtract 4 from both sides. That'll be 7 on the other side. And now to undo e, remember ln is kind of the special log that lets us get rid of e here because ln and e cancel out. So taking the ln of both sides, I've got 3x ln of e, which we know ln of e is just 1, greater than ln of 7. And when I divide, I can just divide by 3 here. I have x is greater than ln of 7 over 3. Let me go to Desmos and see what that looks like. So we've got ln of 7 divided by 3, and that's about 0.649. At this point, we're going to start solving some logarithmic inequalities. And the process here is kind of the same as the exponential one, only solving a log equation instead of an exponential one. But there is one little catch, because the original function here, log, unlike the exponential function, log has a limited domain. So when we write our solution set at the end, we have to write it so that the input here is a positive value. We need to make sure your log input, whether it's x or x plus 2 or whatever, that needs to be greater than 0 as part of your answer. So with that in mind, pause the video and see if you can get the whole solution set to this. So in this situation, I'm just going to raise 10 to both sides because this is log base 10. So that'll give me x on the left side and then less than or equal to 100. So that's part of my solution. But now we said that our input for my log has to be a positive number. So I also have to write for the domain that this x here has to be greater than 0. That gives me a final combined answer of 0 less than x less than or equal to 100. We'll do one more problem here. On this one we have ln of 3 greater than ln of x plus 2. So pause the video and try this one out. So I'm going to raise e to both sides to get rid of those ln's. And again, I don't have to reverse the inequality at this point because I haven't multiplied or divided by a negative. There is one other little situation that we'll talk about in a minute. But for now, we have 3 greater than x plus 2. So I'm going to subtract 2 to get x by itself. Now when I do that, I'm going to have 1 greater than x. But I don't like having x on the right side here, so I could switch that to write x less than 1 if I read it in reverse order. So I reversed my inequality here because I switched which side that the variable was on. And my other thing I have to be careful of again is the domain. This x plus 2 needs to have a positive value, needs to be greater than 0. So that means x has to be greater than negative 2, in addition to being less than 1. So to combine all of that together, we can say negative 2 less than x less than 1. So that is it for this monster lesson on exponential and logarithmic equations and inequalities. Thanks for coming along for the ride. Until next time, Mr. Sutton signing off.